Welcome to Brain Vision.
Okay, so we're doing chapter 37, problem 84. So we have electrons accelerated by a potential difference of 12.3 volts. This is our delta V. And they pass through a gas of hydrogen atoms at room temperature. What wavelengths of light will be emitted? Okay, so this potential difference applied to electrons are going to give them kinetic energies of 12.3 electron volts. So it is possible to provide this much energy to the hydrogen atoms through collision. So from the ground state, the maximum energy of the atom is negative 13.6 eV plus all the kinetic energy that we could give, which is 12.3 eV. And this corresponds to a negative 1.3 eV energy. So we can look at the hydrogen energy diagram, or figure 3726. And we see that this means the atom could be excited to the n equals 3 state. So the possible transitions when the atom returns to the ground state are either n equals 3 to the n prime equals 2, n equals 3 to an n prime equals 1, or n equals 2 to an n prime of n equals 1. So these are all the different transitions of the hydrogen going back down to the ground state. So these are the wavelengths, or these are the different transitions that produce photons. And we want to figure out what wavelengths these photons are. So we can calculate the wavelengths by using equation 3715. So first of all, the wavelengths from n equals 3 to n prime equals 2, we write as lambda 32 here. And this is given by hc over E3 minus E2. Okay, so we can look at the energy diagram to get these values, but hc is 1240 eV nanometers, and E3, if we look at it, is negative 1.5 eV, and E2 is negative 3.4 eV. So if we plug that in, we get a wavelength of 650 nanometers. So there's the first possible wavelengths. Now we can look at lambda 31. So this is hc over E3 minus E1. So we have 1240 eV nanometers over negative 1.5 eV minus negative 13.6 eV. Okay. So if we plug all that in, this comes out to be 102 nanometers. Awesome. And lastly, the last transition we have available is n equals 2 to 1. So lambda 21 here is hc over E2 minus E1. This is 1240 eV nanometers divided by negative 3.4 eV minus negative 13.6 eV. Cool. If we plug this in, we get an answer out of 122 nanometers. So these are the possible wavelengths that will be emitted, 3 different ones.